Hello, everybody. My name is Michal Oszmaniec, and I'll be presenting our work on a new scheme for quantum computational advantage that uses fermions. Uh, uh, First, I'd like to thank the organizing committee for putting forward TQC despite the pandemic times. Second, I would like to express my gratitude to the program committee for letting me present this project. So, this is a work I did together with Ninnat Dangniam, that used to be a postdoc in my group in Warsaw, Mauro from Technical University, Sydney, Zoltan Zimboras from Wigner Institute in Budapest. Sometime back, we put paper on archive. You can go and check it out. Yeah, let me get started. I begin with introducing very briefly the concept of quantum computational advantage or speed up. We all know that present-day quantum computers are noisy, imperfect, and not yet scalable. They're getting better and better, but we are still far away from fault tolerance. So, in the light of this, a paradigm of quantum computational supremacy was proposed that aims to propose some tasks, some problems for which restricted purpose quantum machines could offer speed up over classical computers. And typically such problems, they have the form of sampling problems. So we have some quantum circuit V that produces outputs X distributed according to some probability distribution, some target probability distribution. And the classical simulator that is supposed to mimic the behaviors of the system samples from some other probability distribution Q. And we say that it approximates the behavior of the machine in the relative error if probabilities are difference of probabilities like are related is upper bounded by the like if we have relative error in probabilities, we also have additive error between probability distributions corresponding to total variation. And now, very broadly, the idea of quantum computational advantage schemes is that you start with the assumption that there exists an efficient classical sampler that, for some class of circuits V, samples from probability distribution that approximates the target probability distribution in relative or additive error. You throw in some mathematics, some conjectures, and you arrive at the conclusion that polynomial hierarchy, which is this hierarchy of complexity classes, collapses. And it's considered to be an unlikely outcome in the light of theoretical computer science. And the main experimental platforms that realize this paradigm are random circuit sampling and boson sampling. So the former refers to just applying sequences of random gates in a multi-qubit system and measuring in the computational basis. Boson sampling refers to the process when we have scattering of input multi-photon Fock states in the linear optical interferometer. And both of those schemes, they were experimentally demonstrated recently. Random circuit sampling by Google. Gaussian version of boson sampling was demonstrated last year in the group of Jawei, Pan, and Heifei. Still, those schemes, they have issues because we cannot certify them in the black box setting. They have to compete with better and better classical simulators that are out there, and there are varying guarantees for computational hardness of those. Now I move to what we propose in the project. Namely Fermion sampling with magic input state. So we have the circuit, fermionic linear optical circuit that produces outputs from some probability distribution. The circuit is initialized in tensor product of so-called magic fermion input states. Those states can be prepared very easily. They operate, let's say, on the space of 4 qubits. And the circuit is either passive fermionic linear optical transformation or active fermionic linear optical transformation. So for both classes, we independently show results. And here are them. So we prove anticoncentration property of output probabilities in this scheme, and average case hardness of output probabilities. So those two are some technical features of the scheme that are like guarantees for hardness of sampling. We also show that it's possible to efficiently certify an unknown fermionic linear optical transformation. Let me introduce the framework of fermionic linear optics. So we have the system of fermions in D modes. The Hilbert space of interest is the fermionic Fock space, which is a direct product of spaces with fixed number of particles, fixed number of fermions. We have here canonical creation and annihilation operators that have anti-commutation relations, fermionic anti-commutation relations. We can construct Hermitian versions of them, so-called Majorana fermion operators. Hilbert space of interest is spanned by Fock states that have definite particle numbers in different physical modes. And passive FLO is a class of transformations that transforms creation operations according to unitary transformation when this unitary acts in the space of modes. In the first quantization, we can understand this transformation as applying the same unitary to each particle. And it's a representation of unitary group in dimension D in this big box. Active FLO is analogous transformation, class of transformations, but we have orthogonal transformations of Majorana fermion operator. Okay. And you can also understand such unitaries as general transformations that are obtained by quadratic Hamiltonian, quadratic in Majorana fermions Hamiltonian. And it's also a representation of now special orthogonal group in dimension 2. Now, we actually want to map system of fermions into qubits because it's not actually easy to make fermions like non-interacting because they are typically charged. And yeah, so we propose to use qubits to emulate their behavior. So we have Jordan-Wigner mapping that does this for us. So system of the fermionic modes is mapped into the qubits. Fermionic Fock states are mapped into computational basis states. Majorana operators are mapped into particular strings of Pauli operators. Importantly, particle number measurements, they correspond in this mapping to computational basis measurements. And local particle preserving quadratic Hamiltonians are actually generated by very specific local on one dimension Hamiltonians like this. So because of this, we can actually implement our class of transformations in superconducting qubits quite easily. to this end, we use well known from quantum optics decompositions of unitaries or orthogonal transformations. So you can decompose arbitrary unitary transformation into concatenation of operations that act just on two neighboring modes. The same, either in this rectangular scheme or in the triangular scheme. So because of this this mapping I was telling you before, when you now represent those transformations in qubits, actually those rectangles are mapped to just 2-qubit gates. Okay, so we get that arbitrary FLO circuit can be realized in depth scaling linearly with the system size in one-dimensional architecture. And importantly, the gates that we have here, they are native to superconducting architectures. So those are like those gates like square root of I swap, single qubit Z rotations, and they were actually already used in quantum chemistry such VQE experiments, for example, performed by Google. I apologize for that. Somehow it should have worked. Oh gosh. Carried out by Google. Sorry, Google, for this. So that was the setting, and I argued that it's feasible. It's not crazy to experimentally implement our scheme. But now I move to our first result, namely the fact that we can efficiently perform tomography of FLO circuits. So we start with an unknown FLO transformation V, and we do the following: we feed it with very specific single separable states. So we have either X plus state or Y plus state in the specific qubit. Otherwise, we have zeros. So we feed in such states. Now, for each state chosen, we are measuring a specific string of Paulis that correspond to one of the Majorana operators, and we do it for different input states and for different measurements that we carry out, and we collect statistics. It turns out, remember that actually this unitary transformation here comes from some orthogonal transformation. So from this statistic, we can get access to this, or we can get estimate of this low-dimensional orthogonal matrix that gives us a proxy for our unitary. And our result is that when you put all the things together, some concentration inequalities, some matrix decompositions, interestingly, we get that for unknown fermionic linear optical transformation, such a scheme allows us to have estimate for the description of an estimate of the FLO unitary V of O, which is epsilon close in diamond norm to the true unitary, with just number of measurement rounds that scales like number of modes to the power 3 over epsilon squared. So this is huge improvement compared to regular tomography that would require exponentially many gates. Now I move to the hardness of sampling of our scheme. So if you initialize your state in free or Gaussian or theta determinant, then it is known that sampling from FLO circuits is actually easy, and it's well known for many years. It dates back to results by Wieland, Gerhard, Vincenzo, and Josa. And one can understand this intuitively because fermionic scattering amplitudes in, let's say, for passive linear optics are related to determinants of submatrices of unitaries that are behind the scattering process. But for bosons, the same amplitudes are given by permanent. And from complexity theory, we know that at least it's conjectured that it's way harder to compute permanence as opposed to determinants. It's in fact sharply hard to compute permanence. So that's why we need to have those magic states, resource states in the input. And a few years back, Dmitry Ivanov from ETH had this nice paper when he showed that actually for passive fermionic linear optics, scattering amplitudes that you have in such a process, they are related to so-called mixed discriminants that are basically superpositions of different determinants. You can understand it quite easily because when you have many input states like this, like you decompose the input into big superposition of stated determinants. So you get this superposition in the output also. And it's possible to show that those combinatorial objects are still sharply hard to compute because one can reduce them to permanent. And also, like from the perspective of quantum computation, it is known that actually active fermionic linear optics can use those guys as resource states and they promote the scheme to universality. From known results, that also gives sharply hard amplitudes of active fermionic linear optics. So, but it's not the end of the story because just computation of specific probability amplitudes, it's not enough to claim the hardness of sampling. So just as if in the worst case specific probability amplitude is hard to compute, it's not in general true that you can approximate that it's impossible to have classical samplers that approximate quite well the output probability distribution. So to address this, people in the field they have the following scheme. So they start from assumption that you have an efficient approximate additive sampler. You then assume some technical property of this probability distribution of over V, so-called anticoncentration. You throw in Stockmeyer algorithm, and this allows you to actually get approximation of output probabilities of your scheme in relative error on average. So for typical V's in the ensemble within the third level of the polynomial hierarchy. And now you throw in another conjecture, namely that it is average case hard to actually approximate to approximate the output probability within two relative error for random V's. So you say that this is actually hard, sharply hard. And if this is the case, you put in Toda theorem, and you get this unlikely conclusion that the polynomial hierarchy collapses. So you need to show this anticoncentration, and you need to show that it's average case hard to approximate output probability distribution, output probability to relative error. So this conjecture has not been proven for any scheme so far. There is just support for this conjecture for various, namely, it's like people are able to show that it's average case hard to approximate output probability distribution up to some small additive error. Now, anticoncentration people know how to show for random quantum circuits, for example, via approximate to design property. Regarding this small additive error for the average case. There was an array of works recently for random quantum circuits, especially the works by Bulan, Azirani, and Movasa. And just this year, after actually after our paper showed up, like there are some results for boson sampling as well. Okay, so what, in the light of all this, what we do in our project? So we study problem of sampling from fermionic linear optics that is fed in by magic input states. And for both classes, we are active and passive FLO. We show anti-concentration. And we show average case hardness of approximating output probabilities within some small additive error. Now I move to what is meant by anti-concentration exactly. So anti-concentration is a property of quantum circuits that that describes the phenomenon in which output probabilities, random output probabilities, when you pick random V's, like with high probability, they don't take values that are too small compared to the mean. Okay, so you know that with significant probability over the choice of V, output probability for specific X, output X0 would be greater than some fraction of that. And we prove something like this for fermionic circuits using Pauli-Zygmunt inequality and estimates on moments of output probability. That we have those estimates via representation theory of unitary and orthogonal groups. And it's actually important because contrary to random quantum circuits, our measure does not form an approximate to design. Actually, numerics shows that when we feed in Gaussian input states, those output probabilities do not anti-concentrate. Interesting remark. How we prove it in hindsight? So we use Pauli-Zygmunt inequality that allows us to lower bound the probability of interest for some random variable X. And as this random variable, we set our output probability, which is the expectation value of effect X0 on the evolved state, evolved via action of our circuit. But now we use the fact that the circuit is actually given by a representation of some low-dimensional Lie group G that has an irreducible representation in our space of interest. So we get that the average is basically 1 over the dimension of this random variable just from Schur lemma. Now, regarding the second moment, we use standard tensor trick, but to expand this, and now actually we realize that those states that you have here, when you when you act with your representation on the computational basis state in the space of interest, those are generalized coherent states of the group in the Hilbert space of interest. And there are some results from group, like from the representation theory of semi-simple Lie groups, that this average then would be just proportional to particular projection onto like very specific irreducible representation in 2 copies of my Hilbert space of interest. So we can evaluate this integral exactly. We can put in this value of average, and it's then just controlled by expectation value of 2 copies of our input state on the projector on this representation. Now, we put it into Pauli-Zygmunt inequality And in the lower bound, we get just ratio of the dimensions, our initial Hilbert space and this irreducible representation I was telling you about. And we have expectation value in the denominator. And actually, it's a lot of, okay, the ratio of dimension you can compute depending on the class of circuits you get, that 1/n to some power alpha, either 1 for passive or 1/2 for the active case. But now it's a lot of effort to upper bound this denominator. But in the end, both contributions cancel out, and you get it that thing is lower bounded by a constant. Okay. Now I move to average case hardness results. So our goal actually here is to construct a low-degree rational interpolation between sharply hard amplitudes in our FLO circuits, and to this that allows us to use polynomial interpolation to recover worst-case probabilities from values of generic probabilities for generic circuits. And to get this rational interpolation, we use Cayley path deformation, inspired by the work of Movasak. So Cayley path is related to Cayley map that maps from the algebra to the Lie group, and it allows you to have basically so you map 0 to identity, and you map some element x in the algebra to some element in the group. You have the inverse also, and when you now connect the 0 and this x, which you take to be inverse image of some gate G, you get in the group rational path between in general between some general worst case circuit G0 and some arbitrary per se element of the group. So now we concatenate this with the representation of interest. So fermionic, like active or passive representation of unitary or orthogonal group, and that gives us a rational, in the end of the day, rational interpolation between worst case circuit and generic circuit in our big fermionic Hilbert. This the degree of this rational interpolation scales quadratically with the system size, with the number of magic states you have in the input. And compared to the previous work of Movasak, we do the Cayley path deformation on the level of Lie group that underlines the problem instead of individual gates. So this is a technical bit. It's a lot of technicalities, mostly sort of applying ideas from Movasak work, but maybe improving them a bit. So our first result is that it's sharply hard to compute exactly values of output probabilities with probability greater than 2/3 plus 1/poly n for random choice of the gates. I apologize for this. The second result concerns average case of approximate computation. I don't really know what has happened here. So so it says that it's sharply hard to compute, to approximate values of this output probability to within some small, polynomially small, exponentially small additive error. Oh, here it is. Sorry, guys. Yes, with probability larger than like 1 minus 1/poly n for random choice of gates. And I should say that our error scaling is worse than the Movasak scaling for the Google layout in terms of size of the system. And recently there were improvements by Bulant and co-authors, as well as Kando and co-authors. And for random quantum circuits, they give improvements of error to this regime. Actual application of their methodology to our setting gives slightly worse error scaling, but improves compared to. Yeah, so with that, I wanted to conclude. We propose new scheme for attaining quantum computational advantage with fermionic circuits and fermionic systems. Because of mapping into qubits, we claim it's experimentally feasible. We gave strong hardness guarantees in the form of anticoncentration and average case hardness of output probabilities. We also showed that it's possible to certify unknown Apollo unitaries efficiently. Just outlook for further problems for the future. I would really want to have genuinely fermionic realization of the scheme, not emulated via qubits. In the interest of time, I just focus maybe on one more potential application of the techniques that we have, namely to scenarios of boson sampling and Gaussian boson sampling. Just one quick advertisement. I'm currently looking for postdoc/quantum software engineer in my group in Warsaw in the field of error mitigation of and characterization of music devices. The deadline is pretty soon, so drop me an email if you're interested. Thank you for your attention.